Hi everybody, Namaste and welcome to Murali's World of Physics once again.
This video forms part 2 of a series of videos on unique numbers in mathematics and physics.
The next important mathematical integer which is important is the so-called Hardy-Ramanujan number, which is 1729. There is an interesting anecdote about the British mathematician G.H. Hardy when he visited the Indian mathematician Srinivasa Ramanujan in hospital. Apparently, Hardy had travelled in a taxi cab which had the number 1729, and he remarked to Ramanujan that this number seemed to be him rather a dull one. He hoped it was not an unfavourable omen. Then Ramanujan replied immediately, No, it is a very interesting number. It is the smallest number expressible as the sum of two cubes in two different ways. Now these two different ways are 1729 is equal to 1 cubed plus 12 cubed. It is also equal to 9 cubed plus 10 cubed. So these are the two distinct different methods by which this Ramanujan number can be expressed as the sum of two cubes. Interestingly, Ramanujan number is neither a prime nor a Fibonacci number. The prime factors of this number are 7, 13 and 90. So 1729 can be written as 7 into 13 into 19. Of course, there are other factors apart from these prime factors. These are 1, 91, 133, 247 and of course the number 1729 itself. Another property is that this number can be written as the sum of three primes in several ways. For example, I have just listed three of them here. 3 plus 5 plus 1721, 13 plus 17 plus 1699, 13 plus 47 plus 1669, etc. This is also the lowest number which can be represented by a what is known as a Gaussian quadratic form, a square plus ab plus b square, in four different ways with a and b positive integers. Now these integer pairs are 25, 23, 32, 15, 37, 8 and 43. 1729 is also the dimension of the Fourier transform on which the fastest known algorithm for multiplying two numbers is based. This is an example of what is known as a galactic algorithm. Now the next Ramanujan-like number is 4104, which can be written in two distinct ways as the sum of two cubes. That is 16 raised to 3 plus 2 raised to 3 is equal to 15 cubed plus 9 cubed. So it is not a Ramanujan number because the Ramanujan number is defined as the smallest number which can be expressed in this particular fashion. Another quite interesting integer is the Kaprekar number 6174. Now this has the unique and interesting property of being the final result of a series of ordered subtractions starting with a given 4-digit number. An example is given here. The first one is the Kaprekar number itself. First from the largest and smallest numbers formed out of the 4 digits. So these are 7641 and 1467. This is actually 7641 reversed. Now find the difference between these two numbers. So it turns out to be 6774 and we are back to the Kaprekar number. So this is the special property of the Kaprekar number. If you proceed along these lines for any given 4-digit number, you will end up after a few steps with the Kaprekar number, and thereafter the pattern is repeated. Now we will try with the Ramanujan number. The largest and smallest numbers are 9721 and 1279. The difference is 8442. Of course, this happens to be the largest number formed out of the 4 digits. The smallest number is 2448 and the difference is 5994. So once again we form the largest and smallest 4-digit numbers formed out of these 4 digits. So these are 9954 and 4599. The difference is 5360. Once again we follow the exercise 6530 and 0356. These are the largest and smallest 4-digit numbers. When you take the difference, wow, the Kaprekar number shows again. This is just another example, 1459. So we follow the different steps. So finally we arrive at 6174, the Kaprekar number itself. Now some special properties of the Kaprekar number. If you sum up the 4 digits, we get 18, and the Kaprekar number can be expressed as 18 raised to 3 plus 18 raised to 2 plus 18 raised to 1. Of course, being an even number, it is not a prime number. The prime factors are 2, 3 and 7. 6174 is equal to 2 raised to 1 into 3 squared into 7 cubed. It is also what is known as a Harshad number, being divisible by the sum of its digits. That means 6174 by the sum of the digits, which was 18 as we have seen earlier. So this division gives an integer, and this number is itself what is known as a palindrome. That means if you reverse this number, it turns out to be the same number. One useful application of the Kaprekar constant is in cryptography. It is used to generate random numbers for encryption and decryption purposes.
Another interesting set of unique numbers are the so-called perfect numbers. Now, a perfect number is a positive integer that is equal to the sum of its factors, excluding the number itself. The smallest perfect number turns out to be 6. The factors are 1, 2 and 3, and the sum of these factors is equal to 6. Therefore, 6 is a perfect number. Now, we don't find another perfect number until we get to 28. The factors here are 1, 2, 4, 7 and 14. Of course, 28 is not counted here. We can see that 1 plus 2 plus 4 plus 7 plus 14 is equal to 28, the number itself. It is seen that the perfect numbers are quite rare. We don't get another one until we go to 496 and then 8128. The next one is an incredibly large number, 33,550,336. The factors of a perfect number are significant as follows. Suppose we have weights corresponding to the factors of a perfect number. Then one can see that it is possible to weigh any object with integer weights up to and including the perfect number itself. For example, consider the perfect number 28 itself. The factors are 1, 2, 4, 7, 14. Their sum is equal to 28. So one can see that we can weigh an object weighing 1 kilo by using 1, 2 kilos by using 2, 3 kilos by using 2 and 1 in combination, 4 using 4 itself, then 5 by using 4 plus 1, then 6 using 4 plus 2, 7 using either 7 or using 4 plus 2 plus 1, and then 8 by using 7 and 1, 9 by using 7 and 2, and so on. So this way one can weigh any object having integer weights up to 28 kilos. Of course, this is not the optimum method for the weighing. If we allow for the weights to be put in both pans, then there is another optimum method which uses only 4 weights. But still, this is one of the methods for doing this. There are other applications of perfect numbers also. For example, in the number theory research, perfect numbers are central to number theory, a field that explores the properties of integers. It's a fertile ground for the development of new mathematical concepts and proofs. In cryptography, some algorithms use perfect numbers in their design. These numbers contribute to the security and complexity of cryptographic systems, making them challenging to crack. Similarly, the pursuit of perfect numbers often leads to discoveries in prime number theory also. There is a branch called algorithm development, and the perfect numbers serve as essential components in various algorithms used in computer science and data analysis. Their unique mathematical properties find practical utility in solving complex problems. Suppose we add up the reciprocals of the divisors of a perfect number n, then one can see that the total adds up to 2. For example, 1 by 6 plus 1 by 3 plus 1 by 2 plus 1 is equal to 2. Similarly, 1 by 28 plus 1 by 14 plus 1 by 7 plus 1 by 4 plus 1 by 2 plus 1 is equal to 2, etc.
The next set of unique integers in mathematics is what are known by the name Fibonacci sequence. These are special set of numbers which have the property that any member of this set can be obtained by adding the preceding two numbers. Now the Fibonacci numbers are represented by the symbol Fn. So therefore the property of these numbers are such that Fn is given by Fn minus 2 plus Fn minus 1. Now this set starts with 0 and 1. So if we apply this property, 0 plus 1 equal to 1 will be the next number in this sequence. Then 1 plus 1 is equal to 2 will be the next number. 2 plus 1 equal to 3 is the next number. Then 2 plus 3 is equal to 5 is the higher number, and so on. So in this way one can construct the entire set of Fibonacci sequence, and in fact this is also an infinite series. So therefore the Fibonacci sequence is 0, 1, 1, 2, 3, 5, 8, 13, etc.
Every third number in the Fibonacci sequence starting from 2 is a multiple of 2.
Similarly, every fourth number in the sequence starting from 3 is a multiple of 3. And every fifth number starting from 5 is a multiple of 5, and so on. Another property of the Fibonacci sequence is that the sum of the n terms of the sequence is given by Fn plus 2 minus F2 or Fn plus 2 minus 1. So this is a general property of the Fibonacci numbers.
Now these numbers have another unique property, and that is the ratio of any member of this series to its predecessor. That means Fn plus 1 by Fn. This particular ratio will approach a finite irrational number, which is known as the golden ratio. The value of this is equal to 1.61803399. That means this particular number, which is represented by 5, the golden ratio, is equal to the limit as n tends to infinity of Fn plus 1 by Fn. Now, to illustrate this golden ratio, let us imagine drawing a straight line with a length L and then dividing it into two parts of lengths A and B such that A is greater than B. Now, if the two lengths A and B are such that the ratio A by B is equal to the ratio of the total length, that is A plus B, to the longer of the two sides, that is A. In other words, A by B is equal to A plus B by A. If this condition is satisfied, then it can be seen that the lengths A and B are in the golden ratio. Let's see how this comes about. So from the given condition, we have A square minus B square minus AB is equal to 0 by cross multiplication. And then if we set, let's say, A is equal to KB, we have K square B square minus B square minus KB square is equal to 0. Or cancelling B square, we have K square minus K minus 1 is equal to 0. Or K into K minus 1 minus 1 is equal to 0. Or finally, we get K is equal to 1 plus 1 by K. So this is a sort of recursive relation for K. Now if we solve the earlier quadratic equation for K, we can easily see that the numerical value of K is exactly equal to the value of the golden ratio 5. In fact, as we have just seen, 5 can also be expressed as a recursive relation, as 5 is equal to 1 plus 1 by 5. This can also be expressed in the form of a continued fraction. That means 5 is equal to 1 plus 1 by, again 1 plus 1 by, 1 plus 1 by, etc. So this is a continued fraction.
The concept of the Fibonacci numbers was introduced by the Italian mathematician Leonardo of Pisa. He was also known as Fibonacci, and this particular sequence of numbers is actually based upon his experimental observations of the population levels of immortal breeding rabbits. Now this diagram gives the breeding pattern of immortal rabbits as observed by Fibonacci, and it also shows the relation to the Fibonacci sequence. So here the number of pairs of rabbits as a function of time in terms of months is reproduced. So you can see that the number of pairs increases in this fashion. First month 1, second month also 1, 2, 3, 5, 8 and so on. So it is easily seen that this pattern reproduces the Fibonacci numbers. Also, this sequence appears in the world around us in many other places. For example, if you count the number of petals on a flower or even the number of spirals on a pineapple, you will generally find the total to be a Fibonacci number. This is the emergence of Fibonacci numbers in petals of flowers. Just two examples are given here. In the first one, there are 5 petals, 5 being a Fibonacci number. Then in this second case, there are 21 petals, again 21 being a Fibonacci number. Even in the case of trees, the pattern of branches have close resemblance to the Fibonacci sequence. Look at this diagram here. This shows the development of the branches of a tree as a function of time. So the main trunk first divides into 2 branches, then each branch again splits into 2 branches, and so on. So in this way, at each stage you can see that the total number of branches follows the Fibonacci sequence: 1, 2, 3, 5, 8, 13, 21, etc. Now there are 2 entities which are closely related to the Fibonacci sequence. These are the Fibonacci squares and the Fibonacci spiral. Now what are these Fibonacci squares? They are nothing but an infinite set of squares with sides equal to the consecutive Fibonacci numbers. This is illustrated in this diagram. So this shows the consecutive Fibonacci squares. So F1, F2, F3, F4, F5, F6, etc. So in each case, the side of the square is equal to one of the Fibonacci numbers. Now Fibonacci spiral is actually a polar plot of the Fibonacci numbers. This will be similar to what we call the logarithmic spiral. In fact, this is a never-ending spiral similar to itself on any amount of magnification.
We will now draw the Fibonacci squares in a 2-dimensional plot, starting with F1 at the origin, followed by F2 above it, then F3 on the left, adjoining and aligned with the first 2, and so on. Next, we draw quadrant circles inside each Fibonacci square, tangential to 2 adjoining sides. This way we get the Fibonacci spiral.
One example in nature is in the case of the nautilus shell. This is the nautilus shell, and you can see a clear Fibonacci spiral emerging in this pattern. Similarly, if you take the case of the human ear, there also, if you look carefully, you can see the Fibonacci spiral being displayed in the shape of the ear. Now, in the case of what are called spiral galaxies, there also you can see the Fibonacci spiral patterns emerging from the shape of the galaxy. Even in hurricanes and tornadoes, many storm systems will follow the Fibonacci sequence. It would be quite interesting to see which of the Fibonacci numbers are also prime numbers. This gives the list of prime Fibonacci numbers in the first 200 Fibonacci numbers. So now the 4th Fibonacci number, namely 2, is a prime. The 5th one, that is 3, is a prime. 6th one, 5, also is a prime. And similarly, the 8th, 12th, 14th, etc. These are also prime Fibonacci numbers. After the 138th Fibonacci number, which is a prime, the next prime Fibonacci number is at serial number 253 and has 53 digits. So indeed, the prime Fibonacci numbers are quite rare.
I will end this video at this point.
If you like this video, kindly click on the like button and share with your friends and relatives, and also with your different groups. If you have not already subscribed to my channel, Murali's World of Physics, kindly do it now. And please don't forget to click on the bell icon so that you will receive notifications in future about my upcoming videos.
I'll be back soon with another video continuing our discussion on unique numbers in mathematics and physics. Till then, goodbye.